Number 10, the late arrival of non-Euclidean geometry. For more than 2,000 years, mathematicians believed that Euclid's geometry was the only possible description of space. Generation after generation, they tried to prove his famous fifth postulate, convinced it had to follow logically from the other four. The idea seemed obvious. There could only be one geometry, one reality, and one way space could exist. No one imagined that an entirely different kind of geometry was hidden within the very foundations of mathematics. Then, in the early 19th century, something extraordinary happened. The brilliant German mathematician Carl Friedrich Gauss quietly developed a completely consistent system of geometry where Euclid's parallel postulate simply wasn't true. Yet, he never published his discovery, reportedly because he feared ridicule from the mathematical community. Soon afterward, Janos Bolyai and Nikolai Lobachevsky independently introduced similar ideas, proving that entirely new geometries could exist without any logical contradictions. The biggest problem was that the new geometries were not compatible with the old Euclidean geometry to any logical contradictions. The biggest breakthrough came in 1854 when Bernhard Riemann introduced an even more revolutionary concept: curved spaces with no parallel lines at all. At the time, these strange mathematical systems were treated as elegant intellectual exercises, beautiful, internally consistent, but completely disconnected from the real world. No one had ever observed a curved universe. Then everything changed. In 1915, Albert Einstein used Riemann's mathematical framework almost exactly as it had been written to formulate his theory of general relativity. The geometry that had once been dismissed as a mathematical curiosity turned out to describe the actual structure of space and time. Gravity was no longer seen as a mysterious force pulling objects together. Instead, massive objects bend the fabric of space-time itself, and everything, from planets to light, simply follows that curvature. The equations had existed for more than 60 years before physics finally discovered that they described reality. Even today, every planet, every star, every galaxy, and every black hole follows those same equations that were created long before anyone knew the universe actually worked that way. And that raises a profound question. If mathematics is nothing more than a human invention, why does it so often describe the universe long before science discovers the evidence? Why do abstract mathematical ideas repeatedly predict reality decades before experiments confirm them? That mystery remains one of the deepest unanswered questions in both mathematics and physics. Number 9. The hidden pattern of prime numbers. Prime numbers are among the simplest objects in mathematics. They're numbers divisible only by one and themselves: 2, 3, 5, 7, 11, and so on. At first glance, they seem to appear randomly, with no obvious pattern governing where the next prime will emerge. For centuries, mathematicians believed that prime numbers were fundamentally unpredictable, a chaotic sequence scattered throughout the number line. Then, in 1859, the brilliant German mathematician Bernhard Riemann introduced an idea that would forever change the way we think about numbers. He wasn't trying to solve every mystery surrounding prime numbers. Instead, he focused on one deceptively simple question: how are prime numbers distributed as numbers grow larger? While investigating this problem, Riemann uncovered a breathtaking connection. He discovered that the distribution of prime numbers appears to be governed by a mysterious mathematical object now known as the Riemann zeta function. Even more astonishing, he proposed a bold hypothesis. He suggested that every non-trivial zero of this function lies on a single vertical line in the complex plane, where the real part is exactly 1/2. Today, this idea is known as the Riemann hypothesis. If it is true, then prime numbers are not random at all. Hidden beneath their seemingly chaotic appearance is an extraordinary mathematical order, one that remained invisible for thousands of years. Riemann published this remarkable idea in his famous 1859 paper on the number of primes less than a given magnitude. Since then, mathematicians have tested the hypothesis with extraordinary precision. Modern supercomputers have verified trillions of zeros of the Riemann zeta function, and every single one has fallen exactly where Riemann predicted. Yet despite more than 165 years of effort, no one has been able to prove that the pattern holds forever. Some of the greatest mathematical minds in history, including G.H. Hardy, Atle Selberg, and countless Fields medalists, have devoted years to solving the problem. None have succeeded. Today, the Clay Mathematics Institute still lists the Riemann hypothesis as one of its 7 Millennium Prize problems, with a $1 million reward waiting for the first correct proof. But this mystery extends far beyond pure mathematics. Prime numbers are the invisible foundation of modern digital security. They protect online banking, encrypted communications, financial transactions, medical records, and nearly every secure connection on the internet. Every day, billions of people rely on mathematical principles that remain only partially understood. And that leaves us with a remarkable question. If the deepest patterns of prime numbers exist with perfect precision, long before anyone discovers or proves them, are we truly inventing mathematics? Or are we uncovering something that has always existed?